Hi everyone. So today we have a short lesson just on the interval of convergence, and we're going to be using the ratio test to actually find the interval of convergence. Now we're looking at specifically power series, so we're looking for an interval where for x at which that series does in fact converge. So the radius of convergence of a power series is the distance from the center C at which the series will converge. The interval of convergence is the range of x values within the series, within which the series will converge. Okay, so let's look at an example. We have the sum from n equals 1 to infinity of 2 to the nth power times x to the nth power all over n. So what we're going to do is we're actually going to set up our ratio test. So the limit as n approaches infinity of the absolute value. Now we're just going to go right into multiplying by the reciprocal. If you don't know what the ratio test is, please watch my other video. So it's a sub n plus 1, which would be 2 to the n plus 1 times x to the n plus 1 over n plus 1, and we're going to multiply by the reciprocal, which is the same as dividing by the original. So n over 2 to the n times x to the nth power. All right, so we have the limit as n approaches infinity of the absolute value of, we can rewrite this as 2 to the nth times 2 times x to the nth times x over n plus 1 times n over 2 to the n x to the n. All right, we get lots of good cancellation. We end up with the limit as n approaches infinity of the absolute value of 2x times n over n plus 1. Okay, now we can evaluate this limit. So this would just be the absolute value of 2x, since the degree of the numerator and denominator are equivalent. Now, in order for this to converge, remember this limit must be less than 1, which means that 2x must be between -1 and 1. Divide by 2. We have -1/2 is less than x, which is less than 1/2. Okay, this is our interval of convergence almost. Now be careful, because you actually have to check the endpoints in order to confirm or say that it's not including -1/2 and 1/2. So what we're going to have to do is do a little check step off to the side. So if I were to plug in -1/2, we have the sum from n equals 1 to infinity of 2 to the n times -1/2 to the n over n, okay? And so we want to check to see if this, in fact, converges or diverges. Well, then this is the sum from n equals 1 to infinity. 2 to the n times -1/2 to the n is -1 to the nth power over n. This one is actually called the alternating harmonic series, and it actually converges. So you can actually use that by name as well, but this also converges by the alternating series test. So it converges, this is the alternating harmonic series. Okay, so we actually do, and I'm going to add a little or equal to on this side, right? Because that one does work for convergence. Now let's check to see the sum from n equals 1 to infinity of 2 to the n times 1/2 to the nth power over n. Well, when we simplify this, we actually end up with the sum from n equals 1 to infinity of 1 over n. This diverges. Oops. So because this diverges, and it's because it's the harmonic series, we don't want to include 1/2 in our interval of convergence. So the interval of convergence is bracket -1/2 to 1/2 parentheses, because we don't want to include 1/2. And then the radius of convergence, remember that's the distance from the center of where it converges to the endpoint, would just be 1/2, because 0 to 1/2 and 0 to -1/2 is 1/2. Okay. All right. So now would be a great opportunity to go ahead and pause here and try numbers 2, 3, and 4 on your own. And then you can check back with my video. Okay, so let's take a look at number 2. We have the sum from n equals 0 to infinity of x plus 1 to the nth power all over 2 to the n. So remember, what we're going to do first is we're going to set up the ratio test. Once we set up the ratio test, we can start looking for our interval of convergence and check those endpoints. So go ahead and set up, let me put a little line here, I'll go ahead and zoom in. We're going to set up our ratio test. So the limit as n approaches infinity of the absolute value of x plus 1 to the n plus 1 over 2 to the n plus 1 times, and then the reciprocal of the original, 2 to the n over x plus 1 to the n. All right, we can clean this up a little bit. We end up with the limit as n approaches infinity of x plus 1 to the n times x plus 1 over 2 to the n times 2 times 2 to the n over x plus 1 to the nth power. All right, let's cancel out some of these common factors. We end up with the limit as n approaches infinity of the absolute value of x plus 1 over 2. Okay, so now we end up with the fact that this would just be x plus 1 over 2, right? And so we know that this, absolute value of that needs to be less than 1. So we have that -1 is less than x plus 1 over 2, which is less than 1. All right, we multiply everything by 2. We get -2 is less than x plus 1, which is less than 2. Subtract 1, we get -3 is less than x, which is less than 1. Okay, so we end up with a possible, okay, so we end up with possible endpoint situations. So we want to go ahead and check those endpoints. Oh, I guess I don't need to do that, but we want to check. Okay, so let's go ahead and we want to plug in -3 and 1. So we want to check -3, the sum from n equals 0 to infinity. -3 plus 1 would be -2 to the nth power over 2 to the nth power. Let's clean that up. We get the sum from n equals 0 to infinity of, we end up with -2 to the nth over 2 to the nth. We end up with just -1 to the nth power. Now, this is just an alternating series. This actually diverges, right? This isn't going to converge. Okay, and so then you could also check you could check 1. You end up with something similar. We end up with 2 to the, so 1 plus 1 is 2 to the nth power over 2 to the nth power. This is the sum from n equals 0 to infinity of 1 to the nth power. Well, 1 plus 1 plus 1 plus 1, that's going to diverge. Okay, now there is a little trick to this problem. And actually, if you noticed, and there's a reason why neither of the endpoints work, you may notice the fact that this is actually just a geometric power series. And you could have rewritten this as x plus 1 over 2 to the nth power. And then you know that your r is x plus 1 over 2, and it needs to be between -1 and 1. And so it would have skipped a lot of steps here. So if you were to recognize that this is just a geometric series, you could skip this entire step of checking endpoints. We actually don't have to check endpoints for geometric series. Now, if you do, you'll still get that they don't work, but it's just something to keep in mind. So this one, your interval of convergence is from -3 to 1. And then the radius of convergence, well, think about what number is between. So we have 0, 1, -1, -2. Whoops, I didn't make that quite long enough. The number between these two endpoints would be -1. Its distance is 2. So the radius of convergence here is 2. Okay, let's go ahead and look at number 3. So this one we kind of threw in here as a trick question. We have n equals 0, or the sum from n equals 0 to infinity of n factorial times x to the nth power. Turns out this one never converges. And it only actually converges when x is equal to 0. And so this one, what ends up happening is you could go through the motions and set everything up, and you end up with n plus 1 factorial times x to the n plus 1 over 1 times the reciprocal of the original. Clean this up. So we can rewrite this as n plus 1 times n factorial times x to the n times x over 1 times 1 over n factorial x to the n. Okay, and so then we have, let's see, some cancellation. Okay. And we have the limit as n approaches infinity of the absolute value of n plus 1 just times x. Well, this actually goes to infinity. So this series doesn't matter, or I guess over 1, right? But it doesn't matter what happens, right? Or what x is. It's not going to converge. So this one, and x equals 0 is a weird case, right? Where you're just adding up 0 plus 0 plus 0, right? But it only converges when x equals 0. So there is no interval of convergence, sorry, and there is no radius of convergence. It would just be 0. Okay, last one that we're going to do is the sum from n equals 0 to infinity of -1 to the nth times x to the 2n all over 2n factorial. So once again, what we're going to do is set up our ratio test, and then we're going to simplify things and then see what we end up with. Okay, so let's go ahead and set this one up. We have the limit as n approaches infinity of the absolute value of -1 to the n plus 1, x to the 2 times n plus 1, be careful with that one, over 2n factorial times, 2n plus 1 factorial, be careful with that one too. Okay, times 2n factorial over -1 to the n, x to the 2n. Okay, then we end up with the limit as n approaches infinity of -1, an absolute value, to the n times -1. This you need to distribute. This would be 2n plus 2. So it would be x to the 2n times x squared over, this is 2n plus 2 factorial. So this would be 2n plus 2 times 2n plus 1 times 2n factorial, right? To get that cancellation. Times 2n factorial over -1 to the n, x to the 2n. All right, let's cancel some stuff out. So these guys are gone. That one's gone. That one's gone. Got my other absolute value bar. Okay, we have the limit as n approaches infinity of the absolute value of -x squared, oops, over 2n plus 2 times 2n plus 1. Okay, let's take a look at this. Now, the limit as n approaches infinity here, this actually always equals 0, regardless of what x is, which is less than 1 always, right? So in this case, the interval of convergence is from -infinity to +infinity. The interval of, there is an interval of convergence, but it always converges. It doesn't matter what x is in this case. Okay, so the last thing that it has here in your notes, where it says note, always check the endpoints for the interval of convergence of a power series unless, okay, it is a geometric power series. And then that's like what we had in example 2. And you actually don't need to use ratio tests to find the interval of convergence for a geometric power series. You can just use the fact that the absolute value of r must be less than 1. Okay, so that is it for today's short and sweet lesson. Only one more, and we are done with sequences and series for Calc BC. All right, thank you guys.